All right, so to kick off our generative AI portion, I'd like to welcome Professor Faiz Ahmed. He is the Career Development Assistant Professor in the Department of Mechanical Engineering at MIT, where he leads the Design, Computation, and Digital Engineering Lab. His research focuses on creating new machine learning and optimization methods for designing complex engineering systems. So he and his team are interested in a lot of the fundamental questions that we're also interested in at the intersection of machine learning and design, such as how algorithms can synthesize high-performance designs to real-world requirements, how algorithms can help discover or create and generate new designs, and how machines can work together with people to create better products. So very excited for this talk. Welcome.
Thank you. Thanks. This is the clicker?
Forward and backward.
Perfect. Thank you. Great. So hi, everyone. I think thanks for the introduction. And today I'm going to talk about this title of From Data to Design, Rethinking Design Synthesis with Deep Generative Models. And I think a common theme since today morning has been more around manufacturing. And what I'll do is in this talk, I'll take a step back and talk about how we think about design, AI, and manufacturing. So just to start the talk, I think I want to get everyone on the same definition of design. And the definition is that most people will not agree on the same definition of design. Design means a lot of different things to different people. Like for someone, it could be aircraft, complex designs, bicycles, additive manufacturing products, a robot design. And a lot of the concepts I'm going to talk about today will apply to the process of design and creating products for different phenomena. So you can apply the same ideas to the domain that you care about. Now, when we talk about design, I often talk to my friend Bill, and he works at a car industry. He's a designer there. And if the design process is defined in a way where you start with the user persona, you define who your customers are, you understand your competition, you do some design parameters, this is what I want to design, you do some concept sketches, 3D rendering, send it to the person who can CAD it for you. They will often send it for some simulations. It could be your CFD simulations. It could be your structural simulations. And finally, you start doing some form of design exploration. And then you repeat the process. Now, this is what we imagine it should be. But in reality, the process is much, much, much more complex. And they really are often frustrated because you take a design, the parameters are large, and then you have to do back and forth to understand the design process. As a result, people often report that they have difficulty meeting constraints. There is time and efficiency loss. But most importantly, if you look at most product cycles, you will see that the new design of a product is often a small variant of the previous design. It's very hard to come up with completely new products just because the design space exploration is hard, and it's difficult to find good, feasible designs that work. Again, I think some of the issues related to this is why is it difficult to create designs? The tools which we use, whether we are talking about CAD tools, SCAM tools, they are often slow and complicated. And they often require a lot of training, engineering training, where just a novice person cannot use them. The design spaces are huge. The number of things you can change are so many that it's not often possible to try all possible parameters. The requirements can be very complex. Like we have requirements not just coming from physics, but also real-world constraints, as well as requirements which are changing with time. Like customers want different things at different times. And finally, most importantly, this idea of knowledge silos. So what knowledge silos means is you have very good designers in some companies. So I worked in Australia in the mining industry, and we had in the railway and mining industry, and we had some people who just knew everything about designing a particular ore car or particular stand. But once they left the organization, that whole design knowledge was gone. So there are these knowledge silos in a lot of different organizations, and there is no general repository of all manufacturing knowledge or manufacturing knowledge to create product X. Now, what I'm going to talk about is how can AI enable humans to create better designs faster, and with a specific focus on deep generative models, or which often people call generative AI. This is a topic we have been working on for a while. And just to give you some examples of where our current generative AI is in the digital world, We can give an example of a rabbit detective sitting on a park bench and reading a newspaper in a Victorian setting, and the model will generate this image from scratch. Now, it has never seen such an image, right? Like, it creates this from scratch and understands what a Victorian setting is to some extent. Similarly, these models have been progressing at, it's an amazing pace. Like these are the images of elephants generated from last year's best model, and this is from 2022. So you can really see the difference in the quality of the images which are being created is, it's amazing. I mean, it's an amazing time to be working in this area. Similarly, other fields, not just images, like generating code, like you can go and write a small code and it will really fix bugs, write comments, autocomplete your code. And that is something which a lot of departments in computer science are grappling with on what do we do, how do we teach our new students with coding skills. Now, and then there is other fields. For example, some people may ask, what is generative AI? And you can see this definition which is being written by generative AI, where it defines a field of AI that uses algorithms to create new and original context, such as text, images, videos, and other media. So, and there is a lot of hype around it. Like, people are saying, Bill Gates says ChatGPT will change the world, make jobs more efficient. Like, there is claims that it's going to increase productivity by a huge percentage. But what I'll talk about is, why can't I use ChatGPT for engineering design? And when I say ChatGPT, I mean general deep generative models. At this stage, what are the gaps, and what are the things we should be thinking about for the future? So the first thing is, on the left-hand side, you're seeing an image of a goldfish car, and it's cute. And on the right-hand side, you're looking at a creative design of an aerodynamic bicycle made of titanium, high-quality image. Can you manufacture any of these products? That's the question, right? Like, you can see that these products really are nice and cute, but they're not really something you can go and manufacture easily. Similarly, the key issue for this is that deep generative models are often not precise. They don't understand the idea of precision, which creates issues. Like in mechanical engineering, we have linkage systems, which is where we want to create a straight line for, like, we want a linkage system which can create a straight line, for instance, and models will give me something which is somewhat straight but doesn't work at all. And I spent a lot of time, I thought, like, maybe I'm not giving the model enough opportunity, so I wrote like a very detailed input of how to create a suspension system, and it came up with this image, which looks very realistic. But then if you really look at it, you will see that there are issues. There are missing lug nuts, there are floating components. And the key issue comes time and again in different areas where these models don't understand precision, and hence they cannot satisfy constraints. And again, this is another issue that I will talk about precision, but I want to qualify this with that there are a lot of challenges. This is the image of the Pope, which is a fake image. A lot of people saw this in a puffer jacket. There are issues around precision, which I'm going to talk about, intellectual property, privacy, ethics, security, data quality, alignment, scalability, stability, explainability, and so on. So what we wanted to do was, we wanted to create designs. And in this case, I'll show you examples of aircrafts, airfoils, bicycles, cars, and so on. And we noticed that these models really lack a few things. For example, first is performance. Unlike a human face, which has no performance which you can associate, we can run simulation models in a lot of engineering design products to understand how well they perform. Novelty is how unique you are. And constraints are can you be, like, depending on the domain, how do you satisfy those constraints? So we've started with the airfoil design example in my research group. And we said, OK, what if we just train an existing airfoil data set and train a standard GAN model? On this side, you see the green dots were the training data. The generated airfoils were, generated airfoils is what you get, which is basically doing what it is supposed to do. It's generating realistic airfoils. But this was not enough, because we wanted to come up with something completely new, something the model has not seen. And in this particular case, I'll not go into a lot of details, but the idea we used was, can we combine this with the idea of determinantal point processes, and physics-based simulations, in this case, CFD simulations. And those CFD simulations tell us how good every airfoil is, and the DPP model tells us how different they are from each other. So the idea is that you are essentially maximizing a volume in a high-dimensional space where the length of the vector is proportional to how good it is. How good it is depends on domain. You can define your goodness on manufacturability, CFD simulation, or something else. And we did that, and when we did that, we immediately found that these models could go outside the box. So here what you're seeing is that it goes and finds these new airfoils which it had never seen. And the darker color shows that it's almost 28% higher quality also. So it could find designs which were better. And the reason it could do that was it could push the boundaries of the design space from what it had seen. And this was very encouraging, and I thought like maybe we can explore this idea further. But one of my friends came and said, why do you need to do generative AI for this problem? We have been solving it using optimization for like decades. Why not just use the optimization? And the answer was, well, why not? We should use optimization, and we should accelerate optimization using generative AI. So in this case, the first thing we did was we learned the model using generative AI. Then we combined it with Bayesian optimization, genetic algorithms, and different types of optimization for a multi-objective problem. And we benchmarked it against the best optimizers which were available. So in this case, the higher you are, the better you are, the faster you get there. That's good. So these were the two FFD and SVD models which performed pretty well for this optimization problem. If I just throw a naive GAN model, it performs as well as the SVD model. And then we have this MOPAT GAN model, which could really go by almost 200% better by going and identifying areas of this design space which were completely novel. So you could really combine all the existing optimization methods and accelerate them using these deep generative models. And then there are other ideas like you don't need to do unconditional generative models. We also worked on conditional generative models, for example, directly generating airfoils by training the model just once and then conditioning it on different performance. This work was published in KDD, where we showed that most existing models don't work very well when there is less data. So if you see here, these are the areas where there is less data, and the model performance just like really goes down. And using some ideas from probabilistic learning as well as like understanding the data sampling process, we could, again, I'll skip all these details. We could really show that we can get the performance much, much lower. Lower is better in this case, as well as low variance for all target performances. And when we thought about it, I mean, this idea of giving a performance target for a generative model to generate designs is effectively equal to an equality constraint. So what you are saying is, this is my design. I want to generate a design. Its f of x should be equal to something, right? And that's f of x could be anything. And there are other types of design constraints. For example, then next we started looking at CAD models. And in CAD models, we wanted to apply inequality constraints. Something is greater than this or something is less than this. And when working on this problem where the entire CAD model was being generated by the generative model, we saw a problem which is very, very common in design. 90% of our data was in a very small design space. 12% of the design space contained 90% of the data. And when we work in like most engineering domains, you will see that pretty much all the data looks like is very similar. It's not very diverse. If you train a model on this, it gives you a false impression of high performance in that very small space. So here you are seeing that the model performs very well, almost 95% in this space where all the data is. So you train and test here, and you think your model is performing well. But if you go in areas where it has never seen data, the performance really goes down from 95% to 40%. And this is a key challenge, because the domains which we work on are often data sparse. And people have to really either collect more data sets, transfer knowledge from other domains, or to come up with statistical models to compensate for this data issue. Great. With that, I wanted to also switch into another issue. When we are talking about data sets, multimodality becomes very important because most models work with a single modality. Either you work with text, like ChatGPT, or you work with parametric data, you work with images. But in design and manufacturing, most data is multimodal. Like when you go to a shop floor, you don't say that I'll only look and not hear, right? Or I'll only read the documents and I'll not see what's happening. You always have multimodal information coming into you. But the data sets we currently have, most of them are unimodal. And as a result, the best machine learning models which we are even developing now are kind of limited by design. And that's a field like, I think that's something which the community should be thinking about on where we want to take manufacturing next and design next. We have been working with this bicycle CAD company called BikeCAD to design bicycles. And this is exactly what we have done is we have developed a partnership with them where we created a huge multimodal data set of bicycles where we can look at a person's dimensions and understand what is the best bicycle made for them based on the designs that have been uploaded on the internet by different frame builders. And this involves looking at generative modeling as well as understanding the physics of the structural integrity and CFD simulations. Great. And again, I think a key factor in this is that not just looking at the images, but looking at parametric information and CAD models to understand the 3D structure of these structures. One challenge with all of these, which you will often see, is this idea of thinking beyond statistical similarity. Because most machine learning models which we see are developed for statistical similarity, which means they are trained to generate things which are as similar as possible, statistically speaking, to our original data set distribution that was given. But in reality, in manufacturing, you have to really think way beyond statistical similarity. In design, you have to think about other things, performance, constraints, diversity, novelty. And unless we change our paradigm of we need to look at other things, the models will somewhat be limited. So just to wrap up, generative models, I think they have a lot of promise about creating better designs, accelerating scientific discovery. And we have been talking to a bunch of industry partners who are looking at these models and are interested in this whole idea. And I already started talking about going beyond statistical similarity, like this idea of how the models are constrained. To give you an image, these are two bicycle frames, which look very similar, but you can see that slight change in one of those frames causes a huge change in the deflection. So it's 0.05 centimeter versus 10.46 centimeter. This few pixel changes can really cause a change, and the generative models don't understand that. And one thing we have been looking at is trying to map this space of metrics that are important for engineering. I already mentioned a few of them: exploration, constraints, performance, and conditioning. And what do we do? Let's say we understand the metrics. If we understand the metrics, we can first quantify how good the models are. But we could also go back and change the existing models for them to kind of promote generating designs that perform well on these metrics. So in this particular case, one problem we had been looking at is the topology optimization. And within the topology optimization, there is this problem of generative optimization, which is using classical SIMP type methods to create designs which are optimized for some structural performance. Now, these methods have been around for a while, and they are great. However, often they do not guarantee optimal solution and are computationally expensive. So we had been looking at, well, what if we already have a lot of optimal structures? We can maybe learn from those optimal structures and create new optimal structures. Now, there is a paper which came out in 2021 called Topology GAN for this, not from our group, CMU. And they performed very well on all the statistical metrics. So the model looked very good. But when we started looking at it from engineering metrics, like compliance error, 48%, volume fraction error, 11%, floating material, which could be you have some floating material, almost 46%, we realized that the few pixel changes can really change the engineering performance between two models. And you have to create models which take into account these metrics and come up with good estimates. So in this case, we created diffusion models which could create, which could not only understand this, but also take into account different physical fields and understanding the physics of it, things like compliance regressor, floating material classifier, and I'll skip some of the details to show the results. Yeah, so in this case, what you see is that we go from 48% to 4% or volume fraction, so we can really improve manufacturability using some of the diffusion models which are catered for engineering performance metrics. And it's not just in distribution, but out of distribution. Can you perform well on something you have never seen before? Great, so yeah, I mean, what we show is that, yeah, we can perform well on these low compliance manufacturable designs, but right now a lot of work is going to much more complex problems for 3D problems and high resolution problems, and where can generative AI help with these problem sets. Something we have often seen is related to the idea which was presented earlier, is that you don't need to pick between deep generative models and optimization. You can really combine the two. And if you combine the two, the performance gains are huge. Like in this, our recent paper from IDTC, we showed that we can get 10x improvements over the sampling time of diffusion models for doing this. Great, so yeah, some of the takeaways were mostly how can we look at these models, combine them with optimization, and learn from the engineering domain. Last but not the least, I wanted to quickly touch upon this idea of linking digital and physical designs. Now, in engineering and mechanical engineering, like machines are very important, and linkage systems. Have people heard of linkage systems? Any mechanical engineers here, by the way? Oh, great, awesome. So people know. So this is my student trying to come up with a linkage mechanism which can create that curve. So there, you can see the process is really, really manual. You have to change things. If you're interested, you can go on our website and play a game. I've tried it in a lot of classes. Most students give up after the first example. There are 5. So you can try creating these mechanisms. And if you look at the state-of-the-art like software tools in the industry, this is the path we want to create. These are the mechanisms it gives. It really fails to come up with very good designs that can meet these targets. And the issue is it's a huge design space with very, very complex constraints. So we started looking into this problem, and we said, first thing we need is data. So we created a data set of where we wanted a lot of mechanisms, 100 million mechanisms, which was created using a very fast solver, and a lot of coupler curves, which was about 1 billion coupler curves. And once we created this data set, we said we could really, the AI models shine when they have seen such complex problems. Just a simple search on the data set could actually solve all these problems pretty accurately. On the top, you have the previous models. Bottom, you can see a naive search. But we wanted to push ourselves. We wanted to say, what if we want to write an entire text like IBM? Guess who the sponsor of the product was? So here is the solution, where we came up with a complex mechanism which can really work with writing IBM using a single motor. And this problem is extremely challenging because first, you're working in continuous and discrete spaces. Second, if you look at just one alphabet and you fix everything, I give you the solutions, only one node, the green spaces are what is feasible. So it's a very hard problem to solve. Everything doesn't work. It locks. It's a very hard optimization problem. Like if I write down the equation of the M, it's about 590 pages of a book. And that's just one alphabet. So with that, I think I wanted to just talk quickly about, and we incorporated manufacturing designs, built this, manufacturable design constraints, and so on. The ideas are really applied to a lot of other areas around mobility, manufacturability, material system topology optimization, and complex systems. Moving forward, I think I wanted to just quickly touch upon this idea of language democratization. Like I don't write poems very well. My wife can attest on it. Like I asked it to write a poem about kinematic design of linkage mechanisms. And it came up with a pretty good poem. Robotic arms with joints so fine, move with grace in a straight line. Machine learning is the key, it seems, and so on. Similarly, in art, you can draw a doodle, and it comes up with fairly good art. So the question I'll present to all of you is, when can we get to a stage where we have design democratization, where people who are not necessarily designed or trained as designers can go and come up with some constraints, and the model can really generate very complex designs. Thank you, and thanks to all my sponsors and all of you for listening. Thank you.
Thank you. I think we have time for one question.
Thank you very much. Thank you. I had a question in terms, I mean, we're at home doing ChatGPT and doing Python code with one prompt and then recipes with the next. And I guess the question is, when you look at the training data for these problems, is it, and historically I'd say AI is, you have curated data sets and proven networks. Yep. Is it better to have more, like in the airfoil example, would it be better to have some car airfoils or, unrelated things? Is that going to make us better to have the unrelated things, to have the poetry along with the Python, or is it going to be more thin networks trained just on the domain? Yeah. Is the secret sauce the mix, or is it distraction?
I think we need both and a lot of it in general. So if you think about generalizability, having different domains and data from different domains can help the model understand connections between them. But if the data sets are very small for each one of them, it will not even learn anything. I mean, we have tried like mixing 5,000 bicycles with 20,000 cars. And we actually tried the airfoil example, which you mentioned. We are working with Toyota Research on it, and it doesn't work very well, because it just doesn't has enough examples of one domain. But if you increase the scale, it really helps in mixing data sets. Great, thank you.
Great. Yeah, thank you so much.
Thanks.